There's a magic formula. Which just takes way too much time. Nonsense, but I think I don't think I overly needed it. I just put it in and then
No, I want to.
With the camera.
Yes. Okay.
I didn't like every single thing. Make sure it's equal.
Yes.
So that's what's important right now.
Okay.
So that's what's showing up. So let's show you again.
Let me try.
Yeah, go ahead and show you how I. So go ahead.
So I haven't really done
And then
most of the work. Do you really think the TAs are going to look at the case part?
And it's uploaded. Camera control.
And that's how you manually adjust.
Okay, I go to this board, then I finish that board. I want this board.
So you do that. We can.
Okay, I can do that.
Okay.
Thank you. Thank you.
I just checked to make sure that it's
Like at least in terms of
Hello everyone.
uploading the work.
Are you okay with the homework one? Do you have any challenge or problem or no? So this connect system, your homework was let's say four selection. You have four selection. You have for the answer, or just one. You should write the answer, or you should choose between four answers. Between four different kinds. Okay. Okay. Now let's try. Let's start our today's session, which is on the fluid mechanic, pressure. So let's go to the shape. iPad.
That sounds like the most you answered.
Okay. Okay. Today we will continue our discussion on the let's say pressure distribution in the liquid. Last session I saw for you, I plotted this triangle for you on the board, and I show you that the pressure distribution inside this triangle is like this. Axial pressure is equal to this normal pressure over the inclined surface, and P at section at the bottom section, which is section Z, is equal Pn plus 1 over 2 rho g delta Z. So oh my God. Today class, pressure in liquids. Yeah. You have
No, I'm just making sure that this is what.
Okay, thank you. Okay, so it is the discussion that we have last session, and today we want to continue our discussion and show that if you have an element of fluid, it is an element in the fluid. This is an element in the fluid. On the left, pressure is P. On the right, and pressure is the force per area. In order to obtain force, we should multiply pressure by area. Okay? The area of the element that pressure is applied, this is called dz, and the other thing is dx. dz, dx, dy. So the pressure force is P dx dz. Pressure on the left side. On the right side, pressure is P plus dP dy dx. So, we have a small element of fluid. The element is so small. Pressure on the right is P. Pressure on the left is P plus partial P partial Y delta Y. We can use Taylor expansion. We use Taylor expansion to obtain pressure on the right. It is P1, it is P2. P2 is P1 plus partial P partial Y dx dy dx dy. Okay. So it is our pressure. So the net force dF in the y direction, dF in the x direction, dF in the x direction is P plus dP dy dx dz minus P dx dz equal dP dy dx dz. So the force is partial p partial x, dx, dy, dz. I should put, pay attention, it is in the negative direction because positive direction is in this way. I should put a negative sign for this one and a positive for the second one. So the result will be negative. Negative dy, dx, dz. So, what does this mean? This means that pressure force is proportional to gradient of pressure. Gradient of pressure appears in the pressure force. Why gradient of pressure appears? Because we take the element very, very small. We take the element quite small. So pressure gradient appears in the force. So in general, if we consider this side and back side and upper side and lower side, we will have our pressure force has three components. So it is dfx. df vectorial. When I put a vector sign or your book, use a bold sign. It is a vector. df is equal minus partial p partial x I minus partial p partial y j minus partial p partial z k. This is the pressure force. Multiply dx, dy, dz. What is the name of these three together? From mathematics. Partial p partial xi, partial p partial yj, partial p partial z k. Gradient. So df is minus grad p delta x delta y dz. df per volume is equal minus grad p. Gradient is a operator that make a function from a scalar to be converted to a vector. So gradient of p is a vector. So F pressure, we show it by F small f. F is minus grad p. So later I will derive for you the Navier-Stokes equation. The Navier-Stokes equation, in that equation you will see that on the right side of the equation, grad p appears. In general, forces is equal minus grad p plus rho g plus F viscous for the shear stress that we discussed later. Pressure, force, we can call this volume force or volume or weight force. This is shear stress force. Okay? Pressure force, weight force, shear stress force. We have these three forces together. Okay. So I should define for you two other parameter. Gauge pressure. I define two more parameter here. Recording in this class is not very good because that board is not well visible in the recording, but this board is very well visible. So if I want good recording of the board, I should just use this board, but it is very challenging that clean the board many times. Okay, so we define two parameter, gauge pressure.
Yeah, no, I mean, so to be like completely transparent with you, I don't know.
Pressure minus P ambient. This is gauge pressure.
That's why I was asking, because I don't
Pressure minus P ambient. So gauge pressure in this room is 0. Gauge pressure in this room is 0. Because ambient pressure here is pressure ambient. But if we are in the swimming pool and we go down in the swimming pool, gauge pressure is a positive value. Pay attention. Grad P has a negative sign. So when you go down, your pressure increases. When you go down, your pressure increases. So in the swimming pool, if I am in 10 meter depth in the swimming pool, my pressure is greater than P ambient. If I am in 20 meter in the swimming pool, it is much greater than 10 and ambient. Okay? But in this room, gauge pressure is 0. It is easier because we omit ambient pressure in our calculation. P vacuum pressure. Vacuum pressure, P ambient minus P. We don't work with vacuum pressure quite often, but with the gauge we work a lot. Let's go to our swimming pool or okay? We are here in swimming pool. What is the we call it Z. Let's go to the equation on the left. F. F is equal minus grad P plus rho G plus F viscous. From Newton's second law, what is F equal to? From Newton's second law, what is F equal to? You?
Raw times acceleration.
MA.
Well,
Yeah, it is defined, yeah, you are correct. It is defined by, divided by V, you are correct. MA, it is, because this F is force per volume, so you are correct. MA. If we assume the flow is static, the flow neither move nor has an acceleration. What is this equal? What is this Taylor thing? 0. If we assume, let's write here, a static. We back to a static. We are not in dynamic. Later we go to dynamic. Now we are in a static. Another assumption. There is no viscous force. What appears to this? Vanishes. No viscous force. So, if there is no viscous force, if there is, the flow is in a static condition. In this case, grad P is equal rho G. This is our axis. Z is on the vertical direction. One question. Can anyone spell out for me grad P? Expand grad P for me. We have on the left board. Partial P, partial X. I plus partial P, partial Y. J plus partial P, partial Z. K is equal rho G. Rho G is in which direction? Because it is also force. This is force, this is force. Rho G is in which direction? Z. So it is K. What do you conclude from this equation? We have left side 3 component, right side 2 component. Yeah?
The two other components must be zero.
Yeah, these two are 0. Pressure doesn't change in X and Y direction. Result? These two are 0. So these two vanish. Why you have minus? Okay. Because this force is downward. We should have negative sign here for rho G because this force is downward. Take an element of the fluid. Rho G is downward, so it has a negative sign. Put a negative sign for rho G because it is a downward force. So this is 0. What does this mean? Pressure doesn't change in X direction. X is perpendicular to the plate. So if I am here in the swimming pool, you stand here, you stand near the door. We have the same height. So the pressure on both of us are the same because we are on the same position. I am here, you are here. Our pressure are the same. I am here, you are in the board, in the depths of the board. Our pressure are the same. But I am here, you are swimming here. Your pressure will be higher. Intuitively, why pressure is higher when you swim at A and I swim at the surface? Intuitively. Why? You are here, I claim your pressure is higher. Yeah?
Is more water on top of you?
Yeah, exactly. More water on top of you. So you should tolerate atmospheric pressure. I should tolerate only atmospheric pressure. But you should tolerate atmospheric pressure and the weight of column of, you see, this is the weight of the column of water above you divided by volume. mg is weight divided by E is the rho G. Okay? So, from this equation, partial P partial Z is equal minus rho G. I call rho G gamma minus gamma, a specific weight. Rho G is the specific weight. So partial P partial Z is equal minus gamma. So again, why rho G has a negative sign? Take a look here. G is a vector. G is a vector. What is the direction of G? Downward. So it is negative. Here it doesn't put any negative sign. But when it expands the G, G is downward. G is downward. If you have upward weight, it should be positive. But we have a downward weight. G is directed toward the center of Earth. Okay, so we call it gamma. Now we integrate this equation. Integrate this equation from 1 to 2. Okay? I bring the denominator from left to the right. P2 minus P1 is equal gamma Z2 minus Z1. It is the key equation that we have for our problem. Where is Z1? Z1 is the location you measure P1. Where is Z2? Location you measure P2. So if I put here, take a look here, I put here 1, here 2. How much is pressure at 1? And I put the axis at 1. How much is the pressure at 1?
Atmospheric.
Atmosphere. How much is Z at 1? 0. You are correct. So for this one, P2, 2 is here. P2, let me write. So P2 minus P ambient is equal minus gamma Z2 minus 0. So P2 is equal PA minus gamma Z2. I should put the Z direction on positive, on top, not bottom. It is the Z direction. This is correct. Please correct the Z. Z is upward. This has a negative Z. This has a negative Z. Because the correct axis is like this one. X, Y, Z. So P2 is equal PA minus gamma Z2. Z2 is a negative value. Z2 is a negative value because based on our axis, Z2 is a negative value. So negative by negative becomes positive. Gamma of water is 9,800. Rho is 1,000, G is 9.1. 9,800. Multiply by Z. So P2 is equal PA plus gamma absolute Z2. Z2 is a negative because we go downward. if we want to adjust this camera, it take a good time of us. Okay. It's not very easily controllable. So I want to.
It's very delayed.
Yeah, it is delayed, yeah. It's not as fast as I make a comment to it. Okay, keep it like this. Better this board, bad that board. Okay, you need to switch to that board. So the other class that we left and changed was very good because the camera was in front and take both board very good. My other class is better, has better recording. Okay, let's consider this swimming pool, for example, or this dish of water, this bottle of water. Pressure at A, B, C, and D is the same. Why the pressure is the same? Tell me based on the equation I wrote at the end of this board. Anyone who reply? Who want to reply? Take this yeah?
It's the same Z.
Same Z. Yeah, the Z is the same. They have the same. Okay. Now, ask a difficult question. This bottle has water, but this section we have mercury. And mercury has a much higher gamma than water. It is a very dense liquid. Pressure is, compare pressure at C and D with some equation, not intuitively, based on equation. Who can? Yeah?
The pressure at D is going to be greater than the pressure at C
Why?
because the mercury has a higher specific weight, so that for the same amount of Z, it's being multiplied more.
Exactly, yeah. Because pressure at D is Z of here water multiplied by gamma water, Z of this section multiplied by gamma of mercury. Gamma of mercury is higher, but pressure at C is total Z multiplied by gamma of water. This has a higher gamma, has a higher pressure. That is very, that makes sense. Now, so pressure at any, consider this one. This is, we are at B, plus B. Plus B, we are in the air. Plus B, we are in the air. And atmospheric pressure is measured at 0. Here it is 101 kilopascal, 10 power 5 Pascal at this free surface. Question. Pressure at plus P is greater or smaller than P ambient? P0. Pressure at plus P is greater or smaller than P0? With reasoning.
Smaller.
Why?
The Z is smaller. Oh, sorry. Z is smaller at the free surface. So Z
is not smaller. Here Z is 0, here is Z equal plus P.
Yes, yeah.
From this equation, please conclude, Z is positive.
Yes.
It is a negative sign.
Okay.
So P2 is P ambient minus gamma P. Okay? You have a negative here. Because here it is positive altitude. So, question, why the airplane flies at 11 kilometers from the Earth's surface? Why they don't fly at the, for example, 2 kilometers from Earth's surface? Why they go 11 kilometers? When you take a flight to back your home, you see that for example, 10 minutes, 15 minutes, you need to you need to fasten your seat belt for 10 minutes, 15 minutes. Why? Why you need to fasten your seat belt? Why? Yeah?
The less pressure means there's going to be not as much air molecules to resist the plane.
Exactly. Because if I fly here, it is the Earth's surface, it is 11 kilometers. If I fly here, there are higher pressure. I am P ambient. As I go up, the pressure goes down, until I reach that pressure becomes almost constant. So in that case, I have less molecule, as your friend told, less resistant or less drag force, so I can fly faster. I can fly faster. But if this time that you take a flight, please compare the velocity of the aircraft at near the takeoff and at the cruise. At the cruise, the velocity is maximum because there are less resistance. Okay? Yeah?
Is there a certain height where you stop getting like up force on the bottom of the wings? From the...
No, we don't stop. We have, but it is less.
Okay.
It is less, much less.
Okay.
Much less, because the pressure is lower, density is lower, and then the drag force, the resistance decreases. Now, I have a submarine. My submarine moves at -h. There should be a large amount of pressure over my submarine. Why? From the equation. P2 is PA minus gamma Z2. For the submarine, Z2 is -h. Minus by minus plus, P2 is greater than P ambient. Super easy. So if you go up, your pressure drops. If you go down, your pressure increases. One interesting question. I go by plus B here and minus B here. Assume H is equal B. Which one? Go to this side. Gamma Z. Gamma Z. Let me plot over the board. This is the free surface. P equal P ambient. Here I go minus P. Here I go plus P. Here is air. Here is water. Compare gamma Z at 1 and 2. Absolute gamma Z. Which one is higher? Why?
Well, because we have much more pressure from the air and then additional pressure from the water.
No, I don't take care of the first part. I just want gamma Z. Just compare gamma Z.
Well, the second one still.
Why?
Gamma is larger.
Gamma is larger. Gamma is rho G. How much is rho? 1000 multiplied 9.81. Okay? Gamma, it is gamma water. Gamma air. How much is rho? Doesn't write here. 1.25, for example. Multiply 9.81. Okay? So, gamma water is much higher than gamma air. So, the increase of pressure in the water is much more than decrease of pressure in the aircraft that we go upward. Because gamma of the air is 11.8, yeah, 1.25 multiplied 9.8. Gamma of water, 9,700. It is 10 power 1, it is 10 power 3, or nearly 10 power 4. Nearly 10 power 4. 10,000, it is 10,000, it is 10. 1,000 times higher. 1,000 times higher. So the drop of pressure in the air is much less. So aircraft need to go 11 kilometer. 11 kilometer is 10 power 3. 10 power 3 multiplied by 10, it is 10 power 4. It is somehow considerable. It should go very, very high because this gamma is much less. In some references, they ignore, if we are in the, for example, 1 kilometer, 2 kilometer, 100 meter, 100 meter, it is very small if we go 100 meter, 200 meter, 300 meter, very small. The people who go climbing over the very, very top mountain, very high mountains, on the high mountains, they may have problem in breathing. Why?
Lower pressure.
Lower pressure, less oxygen. Okay? The pressure is lower, there are less molecules, there are less oxygen. So the people who go to the mountain should be very careful. This is something that we should take care about pressure. So, okay, this one. It is an interesting example. Assume here is P ambient. If we have a pressure meter, it is a. Does anyone has a? When I was a kid, there was no digital thermostat. The thermometer who measure the temperature of the home and the pressure of the home are not digital. They have a pipe, a small pipe. It is like this one. I remember I had like this one. And inside this, it was mercury. It was mercury, and it is the values. The values were written here. So I can measure both temperature and pressure of the air by this mercury thermometer or mercury pressure gauge. It was a pressure gauge, mercury pressure gauge. And I love this a lot and do a lot of experiments with that. When there was a snow in our outside home, I bring it, put it in the middle of a snow to measure the temperature in the snow and compare with the reporting in the TV. Is the reporting is accurate in our home neighborhood or no? So, okay, it is like that. So, why we use mercury, not water in that? Because mercury has a high gamma and doesn't go a lot with the pressure changes. If we have water, we need a pipe of a few meters. But when we use the mercury, we need a pipe of few centimeters. Because when your gamma is high, your displacement is lower. Your displacement is lower for the same amount of delta P. For the same amount. Assume your P2 minus PA is about 1000, okay, P2 minus PA, because this, let's first discuss this. Here is P ambient, here is P vapor of mercury, because mercury can become vapor here. But we ignore the pressure of vapor of mercury. It is very, very small. Remember the plot I showed for the vapor of water last session. So here is pressure 0, here is P ambient. So, show it Z or yes, Z1. P ambient minus gamma Z1 is equal P mercury, which is 0. So P ambient is gamma 0. Why I use a negative sign? Because I go upward. I go upward. When you go upward, you should, it is or axis. When you go upward, you should use the correct value. The correct value of Z is positive, but the equation on the dashboard has a negative behind it. Okay? So P ambient minus gamma Z1 is P mercury. P mercury is 0. Vapor of mercury is 0. So P ambient is gamma Z1. Okay? So as a result, Z1 is equal P ambient over gamma mercury. Z1 is P ambient over gamma mercury. So Z1 can be is at the order of centimeter. Why it is at the order of centimeter? Because gamma mercury is very high. Gamma mercury is very high. So the thermometer that I had when I was a kid, when I was young, so that thermometer measures the Z1, multiplies Z1 by gamma, and reported me the ambient pressure. The ambient pressure. How much is the pressure in outside? Okay, so this is when it goes up, the pressure drops. Okay? The pressure drops. Okay, so it's gamma mercury. Oh, say gamma mercury is so high. 133 10 100, okay, 133 100 Newton per meter cube. It is gamma mercury. How many times of gamma water? Gamma water is 10 power 4. Gamma water is 9.81 10 power 3. Gamma mercury 1.33 100 10 power 5. Okay, so gamma water is 10 power 4, gamma mercury is at order of 10 power 5. So if I use in my thermometer water rather than mercury, I need 10 times higher height for the thermometer. At the standard, at the ambient pressure, P is 1 atmosphere, P ambient is 1 atmosphere, gamma mercury is at the order of 10 power 5, Z1 is computed as 761 millimeter or 0.7 meter. 0.7 meter. So less than 1 meter. 70% of 1 meter is the edge of the mercury. So if it is we are in the amperes is nearly the ambient pressure is 101 kilopascal. So if you bring a mercury manometer in this class, the edge shows around 0.7 meter. But if we go, for example, to a mountain or high altitude location in the country, this altitude will decreases because the pressure decreases as you go topward. Okay. Hydrostatic pressure in gases. So far, we have liquid. In the liquid, this equation works well. This equation works well. This is our equation. P2 is equal PA minus gamma Z2. It is very well for liquid. But for gases, I don't write the detail because it is time consuming and we don't have enough time. For the gases, if we back to our equation, pay attention, it is our equation. dP dZ is minus rho g, okay? For liquid, we assume rho g is constant. So we take gamma out of integral. Gamma was independent of z. We take gamma out of integral and you see gamma is constant, delta z is z2 minus z1. But for gases, rho varies with pressure. For gases, we have P equal rho RT, equation of state. So dP dZ is equal minus rho g, this equation. This equation. The equation is the same. But, take a look at the board. Here, for liquids, rho is independent of P. Rho is independent of P. So I can integrate left side and right side without any chatting. But for gases, rho and P are connected. So instead of rho, I put minus P over RT from equation of state. And then integrate dP over P, dZ over minus GR, dZ over T. So, it is our equation for gases. The left side is ln P2 over P1. The right side is this equation. The right side, we can assume two conditions to integrate dz over t. The first condition, assume t is constant. So if I assume t is constant, t becomes out of integral. Integral of dz is equal z2 minus z1. So ln p2 over p1 is equal minus g over r t0, z2 minus z1. For p2 is equal p1 exponential minus g z2 minus z1 r t0. So you need this equation. Okay? You just need this equation. If I give you, there is air, isothermal. If I tell you air is isothermal, P at any altitude connected to P at the reference with this equation. So it is a exponential with a negative sign. It is the exponential with a negative sign. Exponentially pressure drops. But assumption of T constant is not a very correct assumption. So when I am here in amperes, temperature is higher than when I go to this mountain. So in this case, I assume T is constant in amperes and in the mountain near amperes. It is not correct. So the researchers, the fluid dynamists start thinking and they thought, okay, let's T drop linearly. It is amperes, it is mountain. T here to here drops linearly with altitude. So assume T is T0 minus Bz, where B is the lapse rate, the rate of decline of temperature. In this case, if we integrate this, we reach to this equation. Pressure at any point is equal P ambient multiply 1 minus Bz over T0 power G over RB. G over RB is 5.26 for air. T0 is the temperature at the surface, like amperes. B is the lapse rate, it should be given to you. And Z is the altitude of the location you want to measure pressure. Similarly for density. you have this equation. Okay, let's solve two examples for you. Let's solve two examples. Or let's go to my own example. My own example is nicer than the example on the PowerPoint. So I solve my own example. Okay, I keep this equation. My example is a bit complex. Example 1. We have this mixture at the top air, at the middle gasoline, at the bottom glycerin. And there are two pipes that measures the pressure of the gasoline and glycerin. It is Z equals 0. The bottom is Z0. We put always the the reference at the lowest point. Here is we call this H. We call this Y. We call this ZC. We call this ZB. Okay? H from the glycerin surface to the entry point of the manometer for B, and Y is from the glycerin bottom to the manometer to point C. Glycerin has a height of 1 meter. This one is around 1.5 meter. This is around 2 meter. So we have this data. The question wants us to find ZB and ZC. Find ZB and ZC. PA is 1 kilopascal gauge. PA is 1 kilopascal gauge. PB gauge equal PC gauge is 0. P at point B and P at point C are atmospheric pressure. So the gauge pressure is 0. Okay? The gauge pressure is 0. I want to know ZB. Pay attention. ZB is here, from here to here. I didn't write here because it is a pipe at the middle. And ZC is from here to here. ZB is the measure of the gasoline in the tube, and ZC is the glycerin in the tube. I start for point B. For point B. I know two pressures. I know P ambient, which is 1.5 kilopascal, and I know PB, which is 0. Okay? So I write this equation from A going down and then going up to B, because I know the both side pressure. PB plus PA. I start from left. I usually start from left. No difference. You can start from right. PA. Take a look here. PA for this point. I go down by 2 meters. In which gas or which fluid I go down? In air. I go down. So I must add to the pressure by gamma air multiply P. Correct? Okay. How much in gasoline I should go down? Pay attention. I want to go to point B. I shouldn't go down by 1.5 meter. How much I should go down? Yeah?
Not distance minus h.
Exactly. Plus gamma gasoline 1.5 minus h. Because I don't go 1.5. Then I am here. I am this point. Take a look. I am this point. Then I start going up. This horizontal, no change. From here to here, I go up. How much I go up? How much I go up? First, I go up. So it should be negative. In which liquid I go up? Which liquid is here? Please tell me.
Gasoline.
Gasoline. Minus gamma gasoline. If anyone tell me the altitude, yeah?
Is it ZB minus H?
You miss one term. Yeah?
Minus h minus 1.
Minus y. Why? I go ZB, it is ZB, this is ZB, okay? But this length is this one. This one is, take a look at me, take a look here. This length, this small length, is ZB minus H minus 1. Just this length. Gamma air is 1 point. It is 12. I put 12 for gamma air. Gamma gasoline is 6670. 6670. 6. 667. Okay, how much is this one? How much is this one? When I PA plus 1 plus minus is equal PB. How much is P1? PB? 0. This is equal 0. This is equal PB equal 0. Any question?
I'm just wondering why you used gasoline twice when you were subtracting. And
Because here is gasoline,
Yeah.
you agree? And here is also gasoline. This I go in this way. Let me plot with another color. I started from here. I go down here, and then go up here. Gasoline, A. Gamma A, gamma. GA, gamma, GA. Okay? Because I am 2 times in gasoline. Okay, how many unknowns I have in this equation? How many unknowns I have in this equation?
1.
No. 2. What are the unknowns? Yeah, H. But we are lucky that H cancel out. Okay? H, positive gamma minus H, minus gamma minus H. So the H cancel out, and I can solve this and find ZB as 2.73 meter. Okay? Let's solve for ZC. You should help me here. We are near the end of class, you should help me. Okay. I want ZC. I do the same. PA, I go down in air, gamma air, multiply 2. Gamma gasoline, multiply how much? Multiply how much? I want ZC. Yeah? 1.5. Here the H is not important. H is for this gauge meter. We are in this gauge meter. Okay. Plus gamma glycerin. Gamma glycerin. How much? How much I should? Yeah. 1 minus 1. Okay, now I should go upward. Okay, let me plot the path. Take a look here. I start here, go down, plus gamma air multiply 2, go down, gamma gasoline multiply 1.5, go down, gamma glycerin multiply 1 minus y, then horizontally, horizontal doesn't change pressure, then go up. The last term, positive or negative? Why negative? Go up. Mine, which comma? Which comma?
Glycerin.
Glycerin. Which altitude? How much is this altitude? ZC minus Y. Is equal how much? 0. Is equal PC equal 0. Okay? So, we have two unknowns, okay? ZC and Y, but fortunately, Y cancel out. Y cancel out. Y and H are some additional that help us to understand better. They are helping equation. So we solve ZC is equal 1.93 meter. 1.93 meter. Okay, thank you. So I will give you homework 2 today based on the course that I teach you today. Thank you. See you on Thursday.
What's the value for a license?
What's the value of budget?
Oh, I saw. It is.
Wow.
12,000. Thank you. You have a class? Other class? I should ask the department if I don't see the camera. Well, I think we have Thank you.
Well, you're just key. You're just, oh yes.
Thank you, Professor.
Yes.